Okay. Ready to start. So today we're continuing on with Chapter 6. And remember that this is the chapter where we're talking about material behavior. So we've got a whole bunch of material functions, which are standardized tests that we're using to evaluate how materials behave. And now we're going to store up some memory about non-Newtonian effects so that when we develop new constitutive equations, we can always take a constitutive equation and predict a material function. Then we're going to need to check those predictions against what materials really do. And so right now we're learning what materials really do. And so we're going to need to come back to these things in order to see whether our models correctly predict the observations. So we spent all this time getting a lot of skills under our belt in order to make predictions from constitutive equations. And now we need to know what we're going to predict them to. So as I said last time, we're going to be talking about a lot of different things, but I'm also going to be summarizing on a sheet what aspects of material behavior are the ones that I consider really important enough for you to sort of know. I hate to use the word memorize, but it sort of will be a case of memorization. But I'm not going to ask you to be able to reproduce for me every small item that's mentioned in Chapter 6. Instead, there's going to be this summary sheet that I'll post on the web at the end of the day so you can print it out, but you can, of course, take notes on it now as well. In fact, this is the summary sheet from spring of '05, and spring of '04's summary sheet is on the web too. They're all somewhat similar, but if you're curious, you can go to the handouts page of our website and see exactly how it turned out in previous years. So I'm going to review using the PowerPoint slides, but I'll start by reviewing using what we've put onto our summary sheet thus far. And thus far we've said that the important material behavior we're talking about is it's different for different materials, but we're going to talk first about steady shear flow of linear polymers. And what we found was that the materials are often shear thinning. All right, the viscosity thins as the rate increases, but that at low rates it reaches a zero shear plateau. And that plateau level is called the zero shear viscosity. On top of that, there's a first normal stress coefficient thinning. It thins more severely than the viscosity, and it comes to a different plateau level. Not necessarily higher, although in the example I gave it was higher. It can be higher or lower, as you'll see in some more data I'll show today, but it typically thins more strongly. And then I skipped ahead in the lecture slides to talk about molecular weight effects. We saw that the zero shear viscosity changes quite dramatically when we change molecular weight. These are on a log-log scale, so these differences are very big, but that the differences at high shear rates are negligible. Okay, so that's a very interesting factor when you think about the design of equipment. Let's say in an injection molding machine, when it's in the extruder and the shear rates are high, the viscosity difference is not important. But then once you take your sample and push it into a mold, it starts to move really, really slowly. And all of a sudden, the viscosity differences are enormous because your shear rates are very low. So you can get a material that seems to be extruding perfectly well, but when you push it into a mold, you get short shots, things that won't fill the molds because the viscosities go up by 2 orders of magnitude because something's gone wrong with the molecular weight in your material. So shear rate effects can be very important in polymer processing. The same kinds of differences are apparent in the first normal stress difference. There's a level difference at the zero shear rate and much less a difference at high shear rate. And then at the very end of class, I showed you this famous Fox-Berry plot of zero shear viscosity versus molecular weight, and this is kind of a key feature that I'm going to talk about again today. So doing that same review on our slides, we're on linear polymers. And the data I showed you were on concentrated polybutadiene. Here's shear thinning of viscosity and shear thinning of first normal stress coefficient. Here's the zero shear effect. Here's the high shear rate effect. Very little difference in high shear rate effect on viscosity. there is some critical shear rate at which the deviation appears that some people make a big deal about. That is interesting to us. It means that two materials that appear indistinguishable will be distinguishable at different shear rates depending on the molecular weights. On the first normal stress coefficient, again, the molecular weight effect is similar. And again, the deviation from where it all turns out to be the same happens at different shear rates. Here's some different data you did not see yet. This is on a polyisobutylene solution. Polyisobutylene is a very long and very elastic type polymer. And this is on a solution called a Boger fluid. It's named after this gentleman, Boger, Professor Boger from Australia. And the Boger fluids were invented to be materials that had a constant viscosity, and sure enough, this does have a constant viscosity, but to have elasticity nonetheless. So this is something just to show to you that if you measure that a material has a constant viscosity, you may not assume that therefore it is a Newtonian fluid. Because here's an example of a material with a constant viscosity, but it has a non-zero first normal stress difference. And that means it's clearly not a Newtonian fluid. Newtonian fluids have, we saw when we predicted it, a 0 first normal stress difference. So non-Newtonian effects come in a bizarre number of combinations. Right? You have to know a lot about a material before you can truly say it's Newtonian or it's power law or it's anything. So this is a material that's called a Boger fluid. It has a constant shear viscosity and a non-zero first normal stress coefficient. And this particular one shear thins, but only in first normal stress coefficient. Now, another aspect about data is that you only know what you see. This constant viscosity is only within this range of shear rates. We have no idea what goes on outside this range. Maybe it's flat. Maybe it starts to shear thin. We don't know. We don't have the data. So that's another aspect. You need to know the entire range of rate of deformation that you're interested in order to say anything about a material. If I had only taken data up to a shear rate of 10, I would have said the first normal stress coefficient was constant for all shear rates, because it was constant for all the shear rates I looked at, but there's always more shear rates to look at. We talked about this when we talked about the last chapter, that normal stress differences cause the rod climbing effect. We did a little example of that. Here's another material. This is a polystyrene solution, also a Boger fluid. It has a constant viscosity with shear rate, but it has a non-zero normal stress coefficient. And this one is the first time I'm showing you second normal stress coefficient. So this is, second normal stress coefficient is opposite in sign to first normal stress coefficient. So in order to plot them on a log-log scale, I can't plot negative numbers on a log scale. Log of negative numbers are undefined. So this is a plot of negative tau, or the absolute value of psi 2, excuse me. And you see that it's about an order of magnitude less than psi 1, which is what we said. So this is two different solutions, one polystyrene and tricresyl phosphate, and one polystyrene and dioctyl phthalate. Those names of those chemicals, if you're curious about them, are in the book. This is figure 6.6 from our book. And so here's a material that never thins, at least in the range of the data that we have, and yet is clearly non-Newtonian because it has these two normal stress effects. And I talked about second normal stress differences, and I showed you this plot before. The second normal stress difference is positive, which gives us a negative normal stress coefficient, and it's about an order of magnitude lower in value than the first normal stress difference. Here are some more data on second normal stress difference plotted a little bit differently. This is from Roger Tanner's book on engineering rheology. These are some water-soluble polymers, and they have first normal stress coefficients. These are plotted with respect to the shear stress. And just to show that there's more data in a variety of forms of second normal stress difference. Notice that these are very steeply varying with normal stress. As I pointed out previously, when we defined normal stress coefficient, it's defined as psi 1 is equal to minus tau 1 minus tau 2 over gamma dot naught squared. And I pointed out that the reason it's squared is because typically tau 1 minus tau 2 goes like gamma dot squared. So if you divide by it, then it'll be a constant. So in order to get this to be a constant, we had to define this as something divided by gamma dot squared. And so we've been seeing that our data, in fact, do come to constant values. But if you plot n instead of psi, you end up with things that are quadratic in either stress or shear rate. Now, all of this data, as I said, is limited. I mean, we've only taken it, let's say, to a shear rate of 100 in this case and down to shear rates of just below 0.1. And that's because there are limits to the measurability of any instrument. It just becomes, stresses become too high, or the flow will not be the flow that it must be. You remember that for steady shear, we prescribe the kinematics. V is equal to the steady shear rate x2, 0, 0. This must take place, or else we're not doing this flow, and we cannot report a steady shear viscosity. So some of the things that can happen in an instrument are shown on this slide. So on the left side are some very close-up pictures of cone and plate flow. So cone and plate flow is a cone that's, I'm exaggerating the cone angle here, but it would be something like this. And the sample is in the gap. So when you look at a full gap, in fact, all of this is filled up with sample. That cone is in the center. So it looks like just a solid bit of material, and that's what I'm looking at both here and here. Okay, there's this top one is actually a narrow, a very, very shallow cone between here and here. And you typically will turn the cone or the plate on the bottom, so it's turning. As you go to higher and higher rates, you eventually get an instability, and this is a picture of that instability. So here you can see that the edge is getting a little messed up, and the sample is kind of coming out of the gap. If you look at it before that happens, the edge dimples in a little bit. So you see this is dimpling in a little bit of a V shape, or a greater than sign at the edge. And once this starts to happen, the flow is no longer steady shear flow. It's doing a three-dimensional flow. The flow, if it's a steady shear flow, will always be in parallel, in sort of concentric cones in the cone and plate apparatus. And when it starts coming out, that's not the flow anymore. So it's those kind of instabilities that limit the upper limit of measurability in a cone and plate instrument. Now, another instrument we can use is capillary flow. So we take a very, very thin pipe. So this is a thin pipe, and we push polymer through it. And polymer comes out. It swells a little bit and then comes out. And this is called capillary flow. And flow through a capillary also is limited at high rates. And it's limited by the kinds of instabilities that are shown here. And I've brought some examples of those instabilities to show you an actual piece of the sample. So this is a piece of polystyrene that came out of a capillary rheometer. And you can see that it's a mess. Okay, it's no longer a nice smooth tube of polymer. It's a completely distorted mess. Here is a piece of polypropylene that shows a very interesting, very regular mess. You can see it maybe even better in the shadow than in the polymer itself. It is a very regular kind of a corkscrew instability that happens on the top of the, maybe you can even hear the zipper effect here. And definitely the shadow is showing that it's a very regular corkscrew effect. So the sample is starting to be a three-dimensional flow. When we solve flow in a capillary, we say it's unidirectional flow in one direction. But if you pump a polymer through fast enough, it starts spiraling out. And so it forms these spiral instabilities. And here's some more polyprop with a much more mild surface distortion, depending on the rate. And this is going to be the hardest one to see. This is a block copolymer And I'm looking at the shadow. Maybe you can see the roughness on the edge. If you come up after class, you can see that there is a very pronounced surface distortion on this block copolymer. It's a very stretchy, elastic material. Sneaker soles are made out of this kind of material. It's not made out of rubber. It's made out of a block copolymer or polyurethane, which is also a block copolymer. And if you try, maybe there at very high distortion, you can see that there are these surface distortions that take place. So even on a soft material, you can get this very distinct distortions. So these flow instabilities are the upper limits. So even though we may want to go to higher and higher rates in our measurements, the material won't allow us. These distortions have characteristic signatures in our measurements. So this, I'll be talking about this when I talk about chapter 10 in detail. But this is a plot of apparent wall shear rate versus apparent wall shear stress in a capillary rheometer. So this blue portion here is the capillary, and then this is the storage reservoir, and sample is being pushed down by this piston, and then the sample comes out at a certain flow rate. And when everything's going well, this apparent shear rate and this apparent shear stress form a very smooth function, and we know formulas that allow us to convert that to viscosity. But every now and then, something like this happens, and this instability occurs. We're increasing the pressure drop, and instead of just increasing normally like we would expect, the flow rate jumps an order of magnitude, and it's called the Spurt instability. So again, imagine you're putting a constant force on this piston. You're moving it down. It's moving polymer through this capillary. You're pushing at a constant stress by putting a constant pressure gas on it or something. And suddenly it just accelerates like crazy, even though you've kept the stress constant. Here I'm at one constant stress. And it just jumps an order of magnitude in shear rate. And that's something that happens because of some kind of instability inside the capillary. All right, so we've already talked about molecular weight effects. And yet last time I introduced you to this plot. This is a plot that summarizes this zero shear effect on zero shear viscosity. So these are eta knots versus molecular weight. So we don't have to say what shear rate it is, because the shear rate it's at is sufficiently low that it's in this plateau region. So all these data have been taken in the plateau region of shear rate. And this is a summary plot of how those zero shear viscosities vary with shear rate. And the part about this I'd like you to remember is that there is a critical molecular weight, and below that weight, this slope is 2, and above that molecular weight, this slope is 3.5. That's a very important and universal, as you can see from this plot, universal aspect of polymer behavior. So that goes on my summary sheet. This hockey stick-like shape, this is a slope of 3.4, and this, excuse me, I said 2, this is a slope of 1. Now, the difference between these two different flows happens because the material passes some critical molecular weight, and that's called M sub c. And I ask a question about this in the next homework. M sub c is called the critical molecular weight for entanglement. So I can explain why this suddenly changes behavior. Below M sub c, we can imagine polymers as relatively short chains. And relatively short chains don't entangle, don't get knotted up. Just like spaghetti. If you had spaghetti that was, very, very short, maybe 5 centimeters long, you could take your fork and just lift it up, and it would never, you would only ever lift up whatever spaghetti was actually on your fork. But if you have long spaghetti and you put your fork into the noodles, you'll sometimes pick up every single noodle on the plate. And that's because one noodle is attached to the next, is attached to the next. They are entangled with each other. And that's the difference. There's a critical length of noodle. There's a critical molecular weight on polymers. Below that critical molecular weight, they disentangle themselves. You pull on them, you pull on one noodle, and the noodle comes out. Above that critical molecular weight, that critical length, you pull on one noodle and many noodles come with it. That's the difference. So that shows up very, very strongly in this zero shear viscosity. Below the critical molecular weight, they're unentangled, and it doesn't take much. You double the molecular weight, you double the viscosity. This is a slope of 1. Above that critical molecular weight, it's much, much stronger. And it really, really is thick in terms of molecular weight. If you double the length, you make the viscosity go up by an order of magnitude. If you double the length, so if viscosity goes like, goes like molecular weight to the 3.4, then if I have one material whose viscosity, whose molecular weight is, say, M1, and I have another material whose molecular weight is 2M1, then the viscosity for this material goes like m to the 3.4. The viscosity of this material goes like 2m1 to the 3.4. So the ratios of viscosities goes like 1/2 to the 3.4. And 2 to the 3.4 is about 10. Okay? So eta 1, 10 times eta 1 is equal to eta 2. Double the molecular weight increases the viscosity by a factor of 10, approximately. Very, very strong difference. All right, moving on to other properties. In addition to molecular weight by itself, molecular weight distribution makes a difference. This is a plot of materials with different distributions of molecular weight. So they all have, materials can have the same molecular weight, can have very similar distributions of molecular weight or very different. And that measurement of molecular weight distribution, narrowness or width of molecular weight distribution, is this MW over MN. If you've taken a polymer class, I'm sure you've seen this number. If you haven't taken a polymer class, let me just say molecular weight distribution is number of polymers, let's say, at various molecular weights. And a narrow molecular weight material would look like that. Its average molecular weight is just about the molecular weight of every polymer in the mixture. If you have a material that has a broad distribution of molecular weight, there are some materials with very high molecular weights. There's some polymers that are very long and some polymers that are very short. And the average molecular weight might be somewhere in the middle. But there's a way of measuring breadth of molecular weight distribution, which is to measure a different kind of an average. Mn is the usual average of molecular weight. Mw is the weight average. You don't need to know this, I'm just telling you. What all you need to know is that Mw over Mn is a measure of molecular weight, breadth of molecular weight distribution. So this is a broad molecular weight distribution, this is a narrow. So this one would have Mw over Mn of about 1. And this one would have Mw over Mn of, let's say, 3 or 4. So even if you have two materials with the same average molecular weight, they can have different breadths of molecular weight distribution. And what that does is it takes a shear thinning viscosity curve, and as you broaden it, it causes it to broaden in how it transitions from the zero shear plateau to the high shear rate region. So these have all been normalized and shifted onto the same scale so that you can just see the effect of molecular weight distribution. And the effect is that for a very narrow material, it's very abrupt between this part and this part. It's fairly abrupt. But for real broad industrial materials, it can be extremely shallow kind of a transition between zero shear and high shear rate. So that's one of my keepers. Page 3 of our notes for the exam. I'm on, let me show you what I'm doing here. This is, A was the linear polymers, long linear polymers. B was molecular weight effect. So I'm under molecular weight effects, and I'm going to add a third category. Well, maybe I'll just call it C. C, molecular weight distribution. And that effect is on a plot of log viscosity versus log shear rate. This is a narrow molecular weight distribution, and this is a broad. So typically, I just ask questions like, which of these two materials has a more narrow molecular weight distribution, something like that. Now, there's another important thing that changes what viscosity we measure, and that's architecture. And what do I mean by architecture? Architecture means, what if we don't have a straight linear polymer? Okay, what if we have little side branches or long side branches like a low-density polyethylene? Or maybe even we have a very compact material like a star polymer. How does that affect what we measure? And the answer is, it's kind of complicated. The linear polymers we've been talking about, let's think of them as those spaghetti noodles. If I pull on it, it can slide out of the constraints that are formed by the other molecules. But if I put a branch molecule in the same situation and try to pull it out with my fork, okay, these long branches can stay tangled up with their neighbors and can slow the material down. So at rates at which this kind of pulling out is effective, these materials have higher viscosities than these. On the other hand, once you get this guy pulled out, or once you get this guy pulled out, they actually behave very similarly. Because once you get them disentangled, they don't tend to remix. So imagine again, if you have a very particular kind of spaghetti that somehow has these branches. If you get them separated out, then they kind of cluster up, and they won't remix very well. And so they become easier to pick one out, pick another out, and just eat them one at a time, let's say. So it's only when they start off really nicely entangled with one another that it becomes very difficult to get them apart. So how that translates into viscosity or rheology is, at high rates, once you get to the point where they're disentangled, they actually just flow like clumps, one over another, and they don't actually have that high of a viscosity anymore because they're not able to entangle with one another. So once you get them disentangled, once disentangled at high shear rates, branch polymers flow more freely. So this is a very complicated situation. I'm showing it to you, and I'm not actually going to put it on, I'm not going to put these plots on our keeper list, just some summary remarks. But it's a very strong function of shear rate, the effect of branching. So at high shear rates, the linear material has higher viscosity at all molecular weights than the branch materials because it's this tangled up thing, higher, but just a little bit higher, okay? Everything has been disentangled, whether it's a linear, three-arm star, which is a three-arm star is the equivalent of a linear branch with one big side branch, and a four-arm star, which is like this kind of asterisk. At high shear rates where they're disentangled, they line up like this. At low shear rates where they're not disentangled, as you increase the molecular weight, the branched ones become extremely viscous because of this entanglement effect. These are going up by 2 orders of magnitude compared to the same molecular weight unbranched material. So the only thing I want to summarize from that is that it's complex. So this is item 2, steady shear on branched materials. So a couple of points. It's complex, and especially at low rates, and at high rates, the polymers disentangle. And this lowers viscosity. Sort of the extreme of branched material is the Dendrimer. This is actually data taken by a guy who got his PhD from Michigan Tech, Srini Uppaluri, from a paper that I wrote with him and his advisor, who's at the Michigan Molecular Institute. And this is on a material called a PAMAM Dendrimer, I've forgotten the name. It's a highly branched material. This is a flattened out version where you have a core molecule, and then every time you add a branch, you branch. So here you have this Y, and on each end of that Y, I've added a Y, and on each end of that Y, I add a Y, and you keep branching out and out. So this is about as organized and as branched as can be, and this has very interesting rheology because it's Newtonian looking, but it has very interesting linear viscoelastic effects at when we get into small amplitude oscillatory shear. So these materials are being used for drug delivery devices and also as rheology modifiers because they're so compact, they help to lubricate long chain molecules to slide past each other and to do that disentangling that helps to lower viscosity. All right, here's another important effect. What happens when you mix something inside a polymer? And this is done very often, either pigments or fillers that are used to reduce the cost of the material, or conductive, let's say carbon, to make the material thermally or electrically conductive. You put some powder into your polymer or to change some other property. And how does that change the viscosity? And there's a classic effect. It's called the filler effect. And the effect is that if you start with, let's say, a polypropylene that's shear thinning, there'll be no effect down here which is not really shown on this graph, but where it's shear thinning and where there's no effect of molecular weight, there's no effect of the filler. But at low rates, so again, when we're filling molds at those low shear rates, there's a tendency for the zero shear viscosity to rise. And it in fact rises until this portion of the curve has a slope of -1. So this is some very, what do we call this, model data, where they've added very well characterized filler material, either a glass beads or a talcum powder. And they show that for a material that's inert, such as glass, you get a slight rise of viscosity, and for a material that has chemical interactions between the particles, you get a more severe rise. So this is worth knowing. This is worth knowing if you ever do work in the field of polymers, because very, very often you're dealing with filled polymers, and if you deal with the processing of filled polymers, you're going to see the filler effect. So this will be my third item to remember, steady shear on filled polymers. And the effect is, so again, viscosity versus shear rate. If you start off with a material that looks like a regular shear thinning polymer, as you add filler, it will tend to do this. More filler added. And this is called the filler effect. And what's important is there's no filler effect at high shear rate. The reason this happens is because at low shear rate, the filler particles and the polymer form various structures. And those structures are very stable. At high shear rate, those structures are completely disrupted. The polymers themselves are disentangled. And it just doesn't make any difference how much filler's in there. It just shears very rapidly in very separate sort of layers. But there's no time during that rapid shearing for any structures to form and persist. But at low shear rate, because you're not pulling them apart very rapidly, they're able to form interesting structures, and those structures have a certain strength, and that's the tendency of the viscosity to rise. On this slide, I make a note of a very good book from 1999 by Ron Larson, The Structure and Rheology of Complex Fluids. It's an entire book, longer than mine, just on these various differences of how materials behave and how that's related to material properties. So if that becomes an interest of yours, I recommend Larson's book. Now, many of you have heard of shear thickening. I don't know that I've mentioned it. I perhaps mentioned it in my undergrad fluid mechanics class. And we usually think that shear thickening might look like shear thinning, but it really doesn't. This is an example of real shear thickening. This is Art Metzner's data of titanium dioxide, so that's a pigment in water. These are suspensions. Shear thinning would look typically like a zero shear viscosity followed by decades-long drop in shear rate. Look at what shear thickening looks like. Shear thickening looks like, well, actually it's shear thinned for a very small, maybe third of a decade, and then it's shear thickened. This is our most pronounced shear thickener, but it also shear thinned, and then it's shear thickened by 3/4 of a decade. So shear thickening is a much less often seen event, and again, a much more subtle effect than shear thinning. It's not too common, and it's due to structured interactions between these particles, the titanium dioxide particles. I'm not even going to include shear thickening on our summary. All right, so just looking back over what I've been writing. 1, steady shear of linear polymers. For linear polymers, we talked about molecular weight, ABC, molecular weight distribution. Item 2, branch materials. So first linear materials, then branch materials. And then item 3, steady shear of fill polymers. My next topic's not going to be steady shear anymore. Well, actually, I have one more, it looks like. Yeah. 2 more topics on steady shear is the effect of temperature and the effect of pressure. I'm not going to put these on our sheet, but I want you to see what they are. The effect of temperature is that as you increase viscosity, increase temperature, the viscosity goes down. And it's a very strong effect. So look, we're going down by decades as we increase the temperature by only factors of, say, additional 30 degrees, very reasonable amounts of temperature change. Viscosity goes down quite a bit. There's a technique called time temperature superposition that allows me to coalesce these curves onto the same graph. And that time temperature superposition is described in the book. And I don't want to take the time to discuss it, but it's a very useful way of being able to interpolate either between temperatures and to predict the viscosity, or to extrapolate to other temperatures what the viscosity curve might look like. Nevertheless, we can definitely see that whenever we measure viscosity, we should certainly do it at a constant temperature. The pressure effect on viscosity can be significant if you go over high enough pressure range. This is the pressure effect of polystyrene and polyethylene. These are very, very high pressures, 150 megapascals. So this would be the difference between atmospheric, let's say, and inside a very fast-moving extruder. Even though we go to the extremes of pressure, we only get 1 decade difference in viscosity. And the effect is more pronounced when there's a big floppy side group on the polymer. So polystyrene has a big benzene ring on the side, and so it has a lot of empty space actually inside its polymer. Makes it a little bit squishier. And so it has a more pronounced pressure effect. And polyethylene is a much more linear polymer, and it has a less pronounced pressure effect. All right, so this is what we've talked about. We've talked about linear polymers, talked about some of the limits of measurability. We talked about molecular weight distribution, branching, the filler effect. And there's more in the book about chemical differences like copolymers, a lot of interesting stuff. And you can look in Larson's book for even more than what I talk about. And then in terms of other parameters such as temperature and pressure, we can summarize by saying that temperature is a very strong effect. Pressure over reasonable pressure changes is not such a strong effect, but it can be important if the pressure differences are very large. My next topic is small amplitude oscillatory shear, and I'm also going to talk about other unsteady measurements. And at the very end of chapter 6, I'll talk a little bit about elongation, but as you already know, we don't have a lot of data on elongational flow. Now, this small amplitude oscillatory shear is a big topic. And being able to read, in some sense, a small amplitude oscillatory shear curve is quite a useful skill. In fact, it's one skill that I would say industry will pay for because so few people have it. What I'm going to talk about, it will be the very bare basics of what kind of information is contained in a small amplitude oscillatory shear scan. And so you'll get a start. If you ever do some experimental work in rheology, you will have to develop more skills in this. And these are very valuable and interesting skills because there's a lot of information. Now remember, I introduced the small amplitude oscillatory shear test as shear flow. We're oscillating, and the main picture was that we could get information about both viscous and elastic properties of a material. And that's why it's so rich. Everything we've talked about so far, not everything, most of what we've talked about so far has been only about viscous effects. How does viscosity change with shear rate? But you can also measure that first normal stress coefficient. If you manage that, you get some information about elastic effects. But I'll tell you, it's a tougher measurement than just measuring viscosity, and so you'll see it less often. But small amplitude oscillatory shear is very easy. In fact, when in the rheology lab, which I teach in the fall, we do small amplitude oscillatory shear second. Because if we did it first, you would think rheology was easy, and I would never maintain interest of the students, I think. They first see how difficult it is to do steady shear viscometry in both cone and plate mode and in capillary flow. And it's dirty, it's time consuming, and cleaning up is quite a challenge. And then they get on the instrument that does small amplitude oscillatory shear, and they're amazed because literally within an hour, as newcomers, they can get data. And that you can see would be very appealing in industry, to be able to get data with somebody who's not very well trained within an hour. And so this data is very, very widely taken. The tricky part is understanding what the data are telling you, and that's what I'm about to try to explain to you. What are the data telling you? And as I said, I'm only going to tell you a little, and the rest will have to come with experience if you do end up working more in this area. So I'm going to talk first about this magical small amplitude oscillatory shear. So the first system we're going to look at, as with steady shear flow, is the very long polymer, a linear polymer. What happens when you do the small amplitude oscillatory shear test to a very long linear polymer? And the answer is, there are some steps I'm leaving out, but if you take the data over a sufficiently wide range of frequency, you can get information about every kind of dynamic behavior of that system. And this is what you get. At very, very low frequencies, you're completely allowing the material to flow. And what the spectra look like is you get the lowest values of these viscous and elastic moduli, and they trend towards very characteristic slopes called, in this zone, which is called the terminal zone. Okay? In the terminal zone, G prime has a slope of 2, and G double prime has a slope of 1. Now, why they have those slopes will not be apparent to you now, but when we study the generalized linear viscoelastic model, we will predict those slopes. They are very understandable to us. Okay? For now, you just have to say, okay, I believe you. At very, very low rates, this is characteristic of a linear polymer. As you go up in frequency, these slopes disappear, and you get a plateau in G prime and a minimum in G double prime. The plateau and the minimum are also very much predictable by linear viscoelastic behavior. This plateau is a result of the presence of those entanglements that we talked about. If there are no entanglements, there is no plateau. Now, as we go up even higher in frequency, there's a very sharp rise. This rubbery plateau is usually about 10 to the 5th, 10 to the 6th Pascal. This rise is representing the glass transition. Now, for those of you who know a little bit about polymers, you've heard of the glass transition. The glass transition is a temperature, and if you go above the glass transition temperature, amorphous polymers melt and are soft. And if you go below the glass transition temperature, they're glassy and hard. This test I'm talking about is a test at constant temperature, so it may seem a little surprising that I'm mentioning the glass transition temperature. But we are doing something that's very much like changing temperature. We're taking a sample, and we're either probing it at very, very low frequencies, or higher, or really high frequencies. When we're probing it at really high frequencies, we're not allowing even a couple of bonds to relax. And so the material stiffens up in some sense and reacts like a glassy material. And so this rise of 3 or 4 orders of magnitude of modulus is the material responding as if it were a glass. And so we characterize it as the glass transition temperature. When you put two materials that have different glass transition temperatures, you can spot it by the position of that regime. So if you have log G prime versus log frequency, there's a plateau up here, which I haven't said yet, but it's almost always 10 to the 9th pascals. And there's this region that goes down to the rubbery plateau, or the entanglement plateau. And this is characteristic of the glass transition. And two materials with the same glass transition temperature will look the same. Materials with different glass transition temperatures will look different. So these two materials that I've sketched have the same entanglement molecular weight and different glass transition temperatures. And then there would be the terminal zone. So you can see that just in this one description of a material, we're able to tell quite a bit about the material. If we had two materials with, and we wanted to know the effect of the glass transition, we could take this kind of data in this regime and see how the glass transition is being affected by changes that we're doing in our system. We could also see about changes in molecular weight and entanglement by changes in this plateau, and I'll talk about that next time. And then where this turns over into the terminal zone is again related to how high a molecular weight the material is, and I'll talk about that some more next time. So we've still got a little bit more to go on Chapter 6. We're one lecture behind because of the snowstorm. I'm going to finish up with small amplitude oscillatory shear and then finish up with the rest of this in our next lecture. And then after that, we're moving on to the power law model, generalized Newtonian fluid. Okay, so have a good and safe spring break, and I'll see you when you get back.